The last thing that we want to do in this lesson is to be able to take a graph of a derivative and use that to construct a possible graph for the original function. And so here we've been given a graph of f prime of x. So this is not f of x, it's f prime of x. How can we go about using this graph to help us graph the original function f of x? Well, they've given me a lot of information in this graph, and one of the ways that we have been consistently making connections among f prime, and f double prime has been by using sign charts. So I am going to set up a couple of number lines below this graph that will function as sign charts both for f prime and f double prime. Alright, so now that I've got my sign charts set up, let me do this. Let me just translate these f prime critical values to this number line. So we have no idea what the actual numbers are, but we just want to identify these as our f prime critical values. And so now it's just a simple matter of asking ourselves, what is f prime doing to the left and to the right of these critical values? So if you notice, this is a graph of f prime, and f prime is above the x-axis to the left of this critical point. What does that mean? It means that it's positive. So I'm going to put a plus right here. Where else is it positive? Well, it's positive to the right of this critical value. That's where f prime of x is above the x-axis. So I'll put a plus right here. Now between these two critical values, f prime of x is below the x-axis, and that means that f prime has negative values. Now as far as my function goes, that means that the original function is increasing, decreasing, and increasing. So we're already getting some clues. Now f double prime is a little trickier because again we don't have a graph of f double prime, but that's okay. What is f double prime? F double prime is the first derivative of the first derivative. So if this is the graph of my first derivative, f double prime would be the slope. So f double prime is actually the slope of this graph at different points. And so one thing I immediately notice is that right here on the y-axis, I have this minimum value for f prime, and that corresponds to a slope where f prime is equal to 0. That means that this is a critical value for f double prime. Now think about the slopes for f prime of x. To the left of this critical point, the slope is negative, and my function, my f prime of x is decreasing. To the right, my f prime of x is increasing because the slopes are positive. I just want to know what are the signs of the slopes for f prime of x. Well, to the left of 0, they're negative, and to the right of 0, they're positive. And since these are f double prime we're talking about, a negative f double prime means concave down, and a positive f double prime means concave up. Okay, so what's going on here? Well, first of all, my concavity changes at 0. That means that this is a point of inflection for my original function f. Notice that my function changes from increasing to decreasing at this critical value for f prime. That means that this is a maximum, which makes sense because it's concave down, so this is the highest point. Here, my original function changes from decreasing to increasing at this critical point, and that means that this is going to be a minimum, which again makes sense since it's concave down. Now, honestly, you can look at what seem to be the approximate values of the slope by maybe drawing a slope graph or slope field and then trying to estimate what those are. That is a lot of work that if we were going to do that, I think they would give us numbers. So in the tradition of curve sketching, we just want to capture this information with something that is representative and meets these criteria. So it's not going to be exact, but that's okay. So let's see what's going on here. We said that we had a max at this critical value. So let's carry that up to a point, and we have a min at this critical value, so we'll carry that down to a point, and we have a point of inflection at 0, and you know, I don't know if that's 0, 0 or some other value. I'm not going to assume that it's 0, 0. I'm just going to put it on the y-axis somewhere. And now what's going on is concave down to the left of that point of inflection, increasing to the maximum, then decreasing to the point of inflection. Here it's concave down, decreasing to the left of this critical value, increasing to the right. And so there is a pretty good facsimile of a function. What are the steps for this? All right, well, let's see what we did. So the first thing that we did was locate the zeros of f prime of x. Okay, so wherever that graph crosses the x-axis, those are the zeros of f prime of x. And the function f has extreme values here. So we don't know if they're minima or maxima until we find out if the function is increasing or decreasing and where. 2. F prime above the x-axis means that f is increasing. In other words, f prime of x is positive. Likewise, f prime below x-axis, these are negative values of f prime, and that means that f is decreasing. At this point, I can go back to these extrema and label them as maxima or minima. Now we get into f double prime. So how do we interpret f double prime? Well, again, remember that that's the slope of f prime. So read f double prime by knowing that f prime decreases, then that means that your f double prime values or your slopes are negative. Likewise, f prime increases implies that f double prime is positive. Now, where f prime of x has a 0 slope, f of x may have a point of inflection. How do I know for sure? Well, I'm going to see the concavity change from across that point. If the concavity doesn't change across that point, then there'll be no point of inflection. So the point of inflection will only occur once we interpret f double prime for the original function to determine concavity. And then finally, number 4, sketch a curve. I'm reluctant to put sketch the curve because yours might look a little bit different than mine, but it'll still meet all of these criteria. It might be a little more exaggerated, this y-intercept might be in a different place. Again, it's not about actually graphing the function. It's about capturing the behavior of the function and analyzing the function's behavior. And so the first thing that I really notice about this is that the original function is a cubic, and it makes perfect sense that the derivative would be a parabola. Because if you apply the power rule to x cubed, you get 3x squared, which is a quadratic. I hope this helps.